This one? This, yeah.
Okay, sorry for the delay, but maybe we should run over a little bit on the other course. We should also extend this break a bit. Good, so summer term also for neurocognitive methods, and as you have realized already, I'm using a different format, so not the workshop format this term, but the kind of weekly seminar/lecture format. I don't know, I mean, in the end, in the workshops after 4 hours, everybody goes to sleep. I don't know what is better. Maybe you have personal. So who likes workshops better, and who likes workshops better? Who likes lectures better? So
I think I know that it's lecture style.
So we use lecture style, and but then of course it doesn't fulfill what actually they want me to fulfill with that you learn all the fMRI methods in the first weeks of scan so that you can read the papers. So that's what other people want me to teach, but that's not possible.
Could I make a suggestion?
Yeah.
Maybe that could be 4 workshops at the length of how many workshops that we have, just 8 hours.
Come on, I mean, in the real world, you guys also need to become adapted to the real world. So in the real world, workshops are always the whole day. And so get used to the real world. But yes, and now we have a lecture series. And the lecture series works that we meet each Monday morning at 10. And then talk about EEG. So the topic is actually EEG, and there is the outline here. So it in a way mirrors a little bit the fMRI stuff, but of course the topic is different, and we will talk about different things. But there is some biology, physics in the beginning, and then there's some content, and then there's more on data analysis. And then some parts of this lecture series will be devoted to open science. So you know that, or maybe you don't know that Ulf Tölch and myself, we last year in the summertime actually did our own seminar on open science. And I want to continue with the open science teaching, and this year I put it into now this lecture series. I think it's important that you get the right work ethic early on in your career, and that we change a little bit of what's going on in science at the moment. So this is devoted to that. At this point, I'm not really clear. That's the story. I'm not really clear whether the topics of open science should also be part of the exam or not. I'm kind of against it because it somehow feels wrong. But then, I don't know. I also haven't scheduled a date for the EEG oral exam because essentially, I mean, I can leave that up to you. I don't know about the other courses. I mean, some of the other courses will change also because Ulf is not teaching that anymore, but you get a more kind of college teaching style by Julia and Adrian this year, which is good. So I don't know when there will be midterm exams or something. So maybe we leave it open for now, but maybe also have a think about. So to me, it actually doesn't matter at all when we do the EEG oral exam. So we can have it. I think I have to make my mind up whether the EEG and the open science are part of the oral exam or only the EEG. Let me make my mind up on that until next week, and then we discuss when the exam will be. It's definitely not before the mid or the end of June, because until then the EEG will run. Yeah? Good. And then, of course, the other thing that is simmering under the surface of this whole thing is, of course, your programming project. So has really nobody looked at that? So who has worked themselves into the programming report and would feel like they would benefit from having a meeting, a workshop or something to clarify details at this point? Or who feels like we should, they rather need more time to figure out things themselves? So who thinks it would be good to clarify questions sooner? Okay, what kind of questions are they? So maybe let's, so you three worked on things. Okay, so let's briefly talk about, have you pre-processed the FMI data? No.
Still working on the bids, converting the bids.
Okay. Yeah, maybe then. Also, so I guess with the bits there will be small questions here and there about details, which makes sense, but maybe also get started on the pre-processing. Of course, you can use non-bits data to do pre-processing, because then more questions accumulate to change. So you should always, this is the reason why one does these things in scripts. It's not that you cannot do something that is from the logical structure after something until you have finished the first thing. So you can, of course, do pre-processing on non-bits data, and then the only thing that you have to change, and this is how you should write your scripts, is that you have to change what specific file goes into the first step of the pre-processing. Right? So it's not that you will then have to rewrite everything once you have figured out the bits. So have you do pre-processing of that data? No. Okay, so I would suggest that you try to get everything up to that you have done what I did this morning, actually, for a single participant, single session, maybe via the GUI, yeah. Maybe not in script form, maybe not with the whole bits, but yeah, I would suggest that everybody has done the GLM analysis of a single subject, single run in non-bits format with the GUI or with scripts until we talk about things, because this is kind of the level I want you to get into before get into that yourself before we talk about it. Because otherwise, like this morning, I will tell you things, and then it's like, yeah, you don't really have the first-hand experience, so you don't really know. So, yeah, continue working on that. There are tons of tutorials also online, and you can just follow. I mean, for the pre-processing and the SPM GLM modeling, you can just follow the SPM manual. The only thing that you need to know is what these onsets are, and if you watch the video again of what I did this morning, then you also know what you can do with these onsets. Yeah. So please work. So this is kind of work on that and get into it, because there's only so much one can teach. This is where you will need the first-hand experience. And you can also split work, right? So you are working in teams. So if you're using the FMI data, then allocate bitsing to one person, pre-processing to one person, and GLMing to one person, and then explain yourself to the other persons what you did there. Yeah? Come on, it will only get, the workload will get more and more and more. The older you get. So just embrace it. Good. So that's then simmering under the surface, and once you have done that, even if you, another option is that you don't do it on the that you don't do it on the data that you now have, but on the example data that SPM provides. Yeah? So SPM provides a lot of example data that you can pre-process and that you can also do GLM modeling on. So if you think it's too heavy and too tricky and too demanding to do that on the data that you're working on, so the checkerboard data, do it on the example data. But until everybody has done that on the example data, and or each group has done it. That's more what I mean. Each group has done it themselves on the surface, on the GUI interface. I think that's then a good point to discuss questions. Yeah. Good. And the deadline for the project report is end of September. Now, please don't tell me you're going to work on it in September. This, I really don't suggest that. This is really the doing the data analysis yourself and learning the methods. This is the best thing that you get out of the whole first year of SCAN. So do it. I can only tell you, you're grown up. Good. Grown-ups. Okay, so the next thing then is introduction to EEG. And this is what we're going to start with. Other questions about the outline, the programming project, anything? No. Good. Then let's go here. Oops. Don't want to do actually downloads. Good. Introduction to EEG. So that's the outline of the course. So of course we start again with some introduction today, and I might also today then talk about electricity and the new origins. And then a big chunk of the course is actually devoted to different forms of event-related potentials, so that you know kind of the basic phenomena that are dealt with in EEG in the time domain. Once you know those, we will talk a little bit more about the basic aspects of EEG, data analysis, acquisition, artifacts, and artifact correction / event-related averaging. And then in the end, we will talk about source space analysis, which deals with the question of how one can figure out where in the brain these EEG signals that you record, of course, on the Skype are coming from, which is our own kind of field in engineering. And we finish then on time frequency analysis, where we talk essentially about Fourier representations of EEG data on a superficial level. The math for Fourier analysis is also actually in my book that will hopefully be finished by the end of the year. So, how does it? Good. Introduction. So these are the books that actually this course is based on, and it's primarily the Luck book. At present, I don't find my second edition. These books are fairly new, so this is from 2005, this is only from 2014, kind of book, and then buy them or one. So the book by Luck, I think the first edition is from 2005. That's the one that I have there. The second edition is just from 2014, I think. That's really, it's kind of the same, definitely has kind of the same style as the Hütte for fMRI. So it's not like statistical methods all on the math that is used to analyze EEG data, but it's really like intuitive and the both introduction to EEG with a little bit of in the Luck book, with a little bit of a focus definitely on event-related potentials, so not that much frequency stuff, and maybe with a little bit of a tinge or a spin into the component and / independent component analysis way of looking at EEG data, which is a specific school which one can like or not like, and so on. So there's a little bit of a political message in the Luck book, and a little bit less of such a political message in the MEG EEG primer by Dahari and Aina Puce, I don't know. The slides are mainly a lot of content is from the LAG book. So I'm actually reading the MEG EEG primer myself these days, or a little bit here and there, and put a little bit from that into the slides for this session, but it might get more. There's also some overlap between them. They're really good reads, and they are really good foundational books to get started with this method. So these are the books. Get them, they're great. EG. So EG is this thing. Sorry. EG is this thing where you put on electrodes, usually in a cap. So this white thing is a cap. You put electrodes over the scalp. These electrodes have these little heads. Maybe I should use this pointer here. So there are these electrodes that have, where you actually, what you see here is mainly the active part of these electrodes. The electrode itself is a little tip on the other side that you basically, by also applying some gel between the electrode and the scalp, makes then contact to the scalp. And if you then turn on the amplifier and the recording machine, what you record are these potential time series from all the electrodes. So here, if you want the x-axis, you have the different electrodes. Here you have the potential, these black lines, and then you see that there's some sizzling around of these potentials. And then, of course, as in fMRI, in cognitive neuroscience, you would then, while you record these data, the participants would do a certain task or get exposed to certain stimuli, or if you're interested in resting brain dynamics, maybe also do nothing at all. Yeah, so that's EEG. We have actually this EEG. This is an active electrode system. We have that over at CCNB. I think I also showed you the room where one can do EEG experiments here. There are many more EEG labs actually in this street down where the other seminar room is. So it is there. You can use it. The nice thing about EEG as compared to fMRI is that it's relatively cheap. So these systems, if you buy them commercially, they are not that cheap, but they're definitely cheaper than the $1 million that you pay for an fMRI scanner. If things break, it's also cheaper. So you don't have this running contract with Siemens that we basically have to pay off every year, although then they provide good service for the fMRI scanner. So it's relatively cheap, and its running cost, you essentially only have this gel, and it doesn't come with all the hassle in terms of the magnetic field is always on, and you have to be very careful. So of course you have to be somewhat careful to not hurt your participant, but you don't have kind of a big hazard in the room where you're actually doing the experiments. So things, at least for me, when I do EEG experiments, they are a little bit more relaxed than for MRI. So relaxed in the sense that I feel better in the MRI environment and always on the tip of my toes, so then nothing goes wrong. And with EEG, you don't have to be that. Only in this room, maybe you have to be. So, has any one of you done an EEG experiment participant-wise? So, who of you has been a participant? Okay, 2 of you participants, and who has done it themselves in terms of collecting EEG data? 1 of you. Like for fMRI, be a participant if there are EEG studies. I'm not sure how many EEG studies there are currently done. We are currently not doing any because we did some last year, but the PhD student, actually who was then a master student, scan master student, so Stefan Appelhof, he's now finishing the paper, but he will hopefully, because he's starting now a PhD with Ralf Hertwig and me over at Max Planck, and he soonish, once he has finished his paper, should be interested in recording EEG data again, so you can all partake in these studies, and then you see the whole thing in action. Yeah, and I think you will also see it in action in Felix's course. That's EEG. MEG is this. Actually, it's more what you see on the left. So MEG, so EEG is electroencephalography. So you measure electrical potentials, electrical currents. With MEG, you measure magnetic fields. And the standard the standard MEG systems look like this. So has anyone been in an MEG system or acquired MEG data? No. We don't have an MEG system here. There are some in Berlin. There are also some in Magdeburg. The thing with this kind of MEG, this is also why this exists now. Some companies actually filed for bankruptcy, so that some companies who built these machines actually don't exist anymore. They are that big because it's a lot of cooling in there, and there are lots of these sensors which are called squids, which is actually shown here. So this is a new room temperate squid, essentially. And this might look a little bit dangerous or something, but it's actually like for EEG, there is no strong magnetic field or anything. So also doing MEG experiments is a little bit more relaxed. I did some MEG experiments back in Tübingen, but since then I also haven't done any. Participant sits in there. It's a little bit more uncomfortable, I found, than EEG. I mean, in terms of the sitting, but on the other hand, you don't have to prepare the electrodes and apply any gel because people just sit in there. This is from a recent paper in Nature, where they actually, some colleagues from Nottingham / Birmingham that proposed to do MEG at room temperature with these new sensors. And kind of the spin on this paper is that you can do it kind of in a freely moving manner. So you might also know that with EEG there's some interest also with respect to virtual reality applications and so on. So there are more and more or less, but there is Klaus Gammann. He has a big lab where people can move around with the EEG system. So there's some interest in this apparently these days, which is not possible, of course, with fMRI. And the same logic in terms of moving around is applied to, it's the spin on this paper essentially. Question then is always, so what is the difference between MEG and EEG? And why is this called Introduction to EEG? So if you ask MEG people, they will tell you a long story why MEG is different from EEG. And of course, physically it's different because it's measuring magnetic fields rather than electrical currents. But you of course also know that magnetic fields and electrical currents are always physically bound together. So whenever you have one of them, you also have the other. Then in this paper, I also wanted to look a little bit what's now, because they say, okay, we can now move around with this MEG system. And I thought, that's great, but you can also do that with an EEG system. So what's the benefit? And in one of their supplementary figures, because they spin the whole thing that you can walk around with this MEG system or do ping pong or whatever. They also compare EEG and their MEG. So here they have this OPM MEG, which is their new MEG system. So the one that you saw on the right with these 4 sensors. So just to make this clear, so these are these MEG sensors, which are all in here. Usually there are 256 in here. And here they have 4 of them over motor cortex. And then they also recorded EEG. And they did something like finger abduction resting, 6 experiments, so 300 trials, 50 trials. And then they did a time frequency analysis. So we will talk about that in the very end of the course. For today, just look at the picture. So that's MEG, that's EEG. And again, that's MEG, and that's EG, that's MEG, that's EG. Well, from my naive point of view, this doesn't look too different. There's something red here, there's something red here, there's something blue here, there's something blue here, there's a little more blue here, which doesn't seem to be here. In the rest, so the point that I'm making here is, yes, they are different, but essentially they're the same. So the whole thing about event-related potentials, which are called event-related fields in MEG, and the whole kind of phenomena that you see with EG, you also see them in MEG, and vice versa, essentially. So from my perspective, not being an MEG researcher myself, I don't have to make a big point about MEG. There are definitely physical differences in terms of how things relate from the brain to the scalp and what you can do in terms of source localization and so on. But roughly these things are similar. So that's why we talk about EG and not so much about MEG. That was the question.
But MEG has better resolution?
You mean spatial resolution? Yeah. Well, you can see that you can see spatial resolution from here because this is a single census or averages over census and time frequency space. Yeah, in a way, that's the rhetoric on MEG that the mapping from the brain surface to the census is less affected by the conductive properties of the skull and the meninges and so on, which is also true, but then you're also only sensitive to certain aspects of the magnetic fields, and I never get it right. I think you're only sensitive to things that happen in sulci and not on the top of gyri, so you have other things coming in. So for all that it's worth, and if you look into the more details, you cannot say MEG is better than EEG. It's looking at different things slightly, but then, like always, you have these trade-offs that if something is better in this thing, then it's a little bit worse in this thing, and so on. So, from my perspective, EEG is perfectly fine, but I also don't want to make a big point of that. But they are quite similar. There's actually work by Rick Hansen on MEG-EEG integration, which you can also do. Of course, you can collect EEG data while you also measure MEG data, and then it gets kind of interesting because then in your data models you have to account. Basically, you can try to, like you always try to do with different data types, to integrate them, and then you have to be more explicit about what you actually think, how the MEG and the EEG come about, and then it gets interesting. But for the level of detail that we talk about in this course, actually MEG and EEG are equivalent. Yeah. Good. So that was a brief nod to the current high-profile paper by Boto and colleagues from Birmingham and Nottingham. It's actually cool people. So it's Karen Mullinger. Matt Brooks is behind the whole thing. He's a cool guy. But I think Andy and me, we would agree that EEG is the future. That's Andy Buckshot, the guy with whom I collected this data that you're now working. So we focus on EEG and start today with the introduction to EEG and a little bit of history. So, which is good to know because EEG is much older than fMRI. So you know that fMRI started in the early 90s and then really became mainstream only in the late 90s. So around 20 years ago. EEG is much older and started already in the 1930s. With EEG recordings, actually what was done before that, we've also seen stuff in the fMRI course on that, is that of course people put electrodes into animals previously, so they recorded since the late 1900 they recorded electrical activity from muscles and nerve cells in animals, and also did recordings of electrical activity on the scalp in animals prior to this. So the story about Hans Berger and starting the EEG, this refers to actually human experiments where Hans Berger put electrodes on the skull, so without any invasive procedure of humans, observed some phenomena and interpreted these as signals from the brain. And this was actually controversial, so people didn't like that at first. So then in the 30s, there were some reports on EEG activity, meaning people put electrodes on the skull of, not on the skull, on the scalp of people and look at the potential recordings. And then in the later on, or in the early 1939, let's say, there were first reports of event-related potentials, which means, and we will talk about that, that you're not only recording baseline activity, so ongoing activity without any stimulus interference, but you provide stimuli. Then, of course, with the war efforts and so on, that field died a little bit out, but then when things look better again, sensory event-related potentials, I think, made their way to the clinic quite fast. So to basically figure out whether something is wrong with some nerve conduction, you can always use event-related potentials. We'll read in the lab book a story about this with respect to auditory potentials, which are actually checked in newborns. But then in the 60s, things got a little bit pushed in EEG research, because people also found out that you can observe EEG activity in an event-related fashion that is connected with cognitive processes. And a big process in this regard, which is then also modulated by the cognitive context, is the P300. So in the 60s, especially the whole P300 cognitive event-related potentials business started. And then more people contributed. I think EEG also got its way into psychology. So most of the psychology departments had then EEG systems. Like then in the 90s, all of them needed to have MRI systems. And of course, what also helped in terms of the EEG data analysis is, of course, the digital revolution, so that you can analyze EEG data much more simple using computers and digitalization, rather than having the EEG written on paper and trying to analyze it like that, which is clear, but then also an important thing. Then I think EEG really has been around for some time. It's used in cognitive neuroscience, and if you ask me, so the hype of fMRI is of course over. So the hype of fMRI was from maybe, let's say, 1995 to 2005 or so. I think that's 2005 was the beginning of this pattern classification business, which was the last big hype in fMRI, I think. Well, after that, resting state took off a little bit more. It's again one of these meta things, but the resting state took off a little bit more after MDPA, but really there hasn't been, now it's layer fMRI, but that's not really established now. So I think the big fMRI hype was between 1995 and 2005. And while this is going on, also there's a resurgence of interest actually in EEG research. So one example is how things worked at the Functional Imaging Laboratory in London. So they, essentially the group of Carl Friston and Ray Dolan, so they started the whole fMRI business big time in the 90s, and obviously contributed to SPM. And SPM was for fMRI until, I think, SPM2, which came out around 2002, 2003. But then also got incorporated, or what they then also incorporated was EEG aspects. And Gareth Barnes, a guy, I think he's also on the MEG paper there, I know from back in Birmingham. He actually only became the MEG person at the Phil in 2009 or 2010. So the Phil only established like a MEG slash EEG full-time unit at the end of the 2000. Which what I'm trying to say is that once more people got into cognitive neuroscience because of fMRI, at one point they also realized, well, there's also EEG, there's also MEG, let's look more into that. So that's kind of the more modern story of EEG. So that, now it's kind of established. I personally, of course, we're doing fMRI work, but and sometimes there are good reasons to do fMRI work. For example, if you're looking at deep structures, like we will also hear today in the CCNB seminar. For other things, especially if you're interested in time and the evolution of cognitive processes over time, then of course EEG is what you want to look at. So a picture from the Hari and Pugh's book. I will call it Pugh's for now. Maybe I should look that up, how she's called. What also has been around, and I think what also you have learned in your undergraduate studies, are that there are these frequency bands in the EEG that you can observe essentially by eye, if you have, of course, the right time axis. And they have also been around forever. So the fact that you get alpha activity if people close their eyes, specifically over dorsal electrodes and in a range of 10 hertz. This is actually linked with the discovery of the EEG. Yeah, so this is not something, although it's kind of frequency analysis kind of thing, it's nothing that only came once people knew or people had the fast Fourier transform algorithm or something, but that was really early on. So and then relating, for example, data waves with sleep. So this is also, of course, what you know, that you can do the sleep stages based on EEG. This has also been around for a long time because it's also very visible on the raw EEG data trace. Yeah? So when I'm doing EEG practicals and showing people that, then of course the first thing to show after some artifacts is alpha, because you can just see it while the data is being recorded. And then you might also know that frequencies above 30/40 hertz are referred to as gamma, and I think this has also died a little bit, but it's maybe still there, and some people still talk about that gamma is consciousness. That was kind of also, this is more like late 90s. I don't think that's the big topic anymore, but some people are still working on it, and of course also believe that. Good. So that's also EEG history, that there are these different frequency bands that one can observe by mere eye. Then let's now look at some basic EEG terminology to get started and clarify terminology. So the first thing is the question, what is the difference between an evoked potential and an event-related potential, and why are these terminologies around? So an evoked potential is an electric potential that is evoked by sensory stimuli. So typical examples are visually evoked potentials, some other sensory evoked potentials. We will look at them. And you can also look at them actually in the data set that you have, because there's also EEG data with checkerboards for visually evoked potentials. Why is now also the term event-related potentials used? And this is straight from the Luck book, where he cites Herb Bogan from 1969. So I just read it. Since cerebral processes may be related to voluntary movement and to relatively stimulus-independent psychological processes, the term evoked potentials is no longer sufficiently general to apply to all EEG phenomena related to sensory motor processes. Moreover, sufficiently prominent or distinct psychological events may serve as time references for averaging in addition to stimuli and motor responses. The term event-related potential is proposed to designate the general class of potentials that display stable time relationships to a definable reference event. So the thing is that the difference between evoked potentials and event-related potentials is more kind of a conceptual difference. An event-related potential to a visual stimulus is, of course, also an evoked potential to a visual stimulus. It's, as we just heard, event-related, the terminology was introduced to also focus a little bit more on cognitive aspects. If you have in mind, have heard in certain talks that people talk about induced or invoked power in terms of frequency analysis, that is something different, and that is something that we will talk about in the end of the course, what the difference is. Here it's only about event-related potentials / evoked potentials. So event-related potentials are electrical potentials associated with sensory, cognitive, or motor events. And this, as a cognitive neuroscientist, should of course be very interesting to you, because sensory, cognitive, or motor events is essentially everything that falls into your realm of expertise as a cognitive neuroscientist. So how do these typical experiments look? And this is a nice example. So this is a typical event-related experiment using what is called an oddball design. Does anyone know what an oddball design is?
For example, if you always show a photo that is like long way and then there's one that is upside down, that would be really odd.
Exactly. So oddball is kind of a colloquial term to refer to the fact that one stimulus class that you define in some way has a high frequency of occurring and another stimulus has a lower frequency of occurring, and then forms the oddball. Here the thing is actually a visual stimulus axis that occur every 1.5 seconds, I assume. Yeah, I think it's 1.5 seconds. There's an X, or sometimes there's an O. People get presented to that on a computer monitor, and the presentation is synced with the EEG system. So the people have an EEG cap on. Their event codes sent to the computer that records both the EEG and these event codes. Of course, these event codes are also in the data files that you have for your neurocognitive methods programming EEG part, if you want to do that. Then you record, let's say, from one electrode here, that's called the active electrode, and then you see when you're recording this, like you would if you would record fMRI data, you record a signal over time. This time it's a potential in microvolt. In MRI, it's the MRI signal. And you know when things happened, just like for the fMRI stuff. And then the typical thing in an event-related potential experiment is that because you know when something happened, what you do is you epoch the data. That means you cut out the data, which is actually shown on the next slide. So you cannot, epoching or segmenting refers to the same thing. So you align, so you cut out things around each stimulus event and then align them in time. So here you have the cutted EEG segments from the stuff before. And of course, if you zoom in, these are discrete samples. So although it's typically shown with a line, these are discrete samples, like you have discrete samples in terms of TR from the scanner, the MRI scanner. And then you have epoch the data, you have these segments, and then the thing that you do is that you average over your segments and then get a response with respect to the onset of one of the conditions, here the onset of the X. So let's zoom in a little bit. That you call an event-related potential, which is here the response to the X's, and here you have the response to the O's. And then the idea is to compare these kind of responses and come up with some meaning for that. Of course, before you do this kind of event-related averaging, you will do some form of pre-processing, which we will also talk about. And actually, Stefan Appelhof, because he's now starting out his PhD on EEG, he looked a little bit into the pre-processing literature, into the pre-processing literature recently, and actually found that there is and has been a little bit of a debate that goes into the direction, if you do different kinds of pre-processing, you will have different kinds of results, which is always good to know. And then, so that's also mirrors what you know about MRI, so that is some kind of pre-processing. Then you do event-related averaging. What hasn't been done, and is still not the biggest topic actually in EEG, but more and more, maybe depending on the researchers, and I'm not one of these people who say we should apply the same statistics that we apply in fMRI to EEG, because I see these kind of curves more as the basis for more interesting dynamic models. But more and more, there's also some statistical modeling of EEG, but it's not traditionally, actually. It comes from a different tradition. So essentially, you end up with these event-related potentials, and then that's essentially it. And then you say they are different, maybe do a little bit of statistics on them. Good. Before I go to the next slide, we should have a break. So let's have a break and continue briefly after 11.